So section 15.7, that's weird. So section 15.7 is on triple integrals in cylindrical coordinates. So I'm going to give you oh, that's just not there. Okay, so I'm going to give you oh, maybe I should have drawn it, but let me actually get another page here. Let me see if I can draw this. I probably can't, but I'll do as best I can. Okay. Okay, so I'll do that later. Okay, so suppose, let me put this down here then. Okay, so for cylindrical coordinates, I do the following. So suppose I'm here in rectangular coordinates. Okay. So what I do here is I measure so I take this point here, X, Y, Z, let's say. Okay. So in this case, Z is going to be the height above, it'll be below the XY plane. Okay. Next, well, maybe I should have done this in red. And now that's going to give me a bad red. Okay, so let's do this in red. So I just project this down into the XY plane. Now, I measure this angle theta and this length R, and then this length Z. So start out at the x-axis, you swing over to the point below this point up here in the XY plane. That gives you the angle theta. The distance from the origin gives you R. The distance above gives you Z. And so you can associate with these rectangular coordinates, cylindrical coordinates, R, theta, Z. Okay. And well, if you look here, these cylindrical coordinates are related to the polar coordinates. In the XY plane, they're just polar coordinates. And so X is equal to R cosine theta, and Y is equal to R sine theta. And in the Z direction, well, they're just the same as Z. And so to convert from polar coordinates into cylindrical coordinates, use this relationship. Now, if you are in rectangular coordinates and you want to write something in cylindrical coordinates, you do the following. Well, just like in polar coordinates, I know that if I divide y by x, I just get r sine theta over r cosine theta. The r's cancel, so we get sine over cosine. So tangent of theta is y over x. And if I square these, I get x squared plus y squared is r squared sine squared plus r squared sine squared. Factor out the r squared, you get cosine squared plus sine squared, which is 1. So x squared plus y squared equals r squared. So this relates x, y, and z to r, to theta. And well, z is just z and z. And so now you can, using these relationships, you can then write coordinates. Now, of course, just like in polar coordinates, there's some arbitrariness here. Obviously, r could be positive or negative, and theta might go around the circle more than once or whatever. So there's some arbitrariness here, but we'll deal with that. You know, we can restrict them if you want. Once we get into an actual physical region, we can restrict these so that they're actually uniquely valued, or well, they'll be uniquely valued in sort of the that make life easy. Okay, so in problem 17 through 28, use cylindrical coordinates. Evaluate the integral over E of Z, where E is enclosed by the paraboloid. So I have here some paraboloid. Z equaling x squared plus y squared, and the plane x equal 4. So it's this region inside here. Okay, so let's try to evaluate this. So I want to evaluate this integral over, let's say, the region E of z dv. Okay, so first off, well, you're going to, let's project down into the xy plane. So I'm going to take some point here, and I want to find this distance here. So we're going to be integrating from z equaling 4 to z equaling, well, z equaling 4 is up here, and z equaling x squared plus y squared is down here. But of course, x squared plus y squared, r squared. And so maybe I'll just sort of note that. Okay. And so we're going from z equaling 4 to, well, z equaling r squared. And so let's do RZ, because I always have to multiply by R. And we're doing integrating dz, let's say dr d theta. Okay. Well, R here goes from 0 out to as far as this circle up here, which has a radius of 4, raised to 2. It's r squared is 4, therefore the radius is 2. So it goes from 0 to 2. And you're going all the way around the circle. So theta goes from 0 to 2 pi. And you just want to integrate that. And so let's integrate that. So this is the integral. 0 to pi, 0 to 2. Integrating z, I get 1/2 rz squared from z equaling r squared to z equaling 4 dr d theta. And now let's evaluate that. So this is equal to integral 0 to 2 pi, 0 to 2. Plug in 4, so that will give you 16. Divided by 2 is 8r minus plug in r squared. Well, r squared squareds are the fourth times r is r to the fifth. And so now let's just integrate this with respect to r. So this is equal to the integral 0 to 2 pi of 4r squared minus 1/12 r to the sixth from r equaling 0 to r equaling 2 d theta. Okay, so let's evaluate this. So integral from 0 to 2 pi. Plug in 2. And so 2 squared is 4 times 4 is 16. 2 to the 6 is 64. Divided by 4 is 16 over 3. Minus plug in 0, you get 0. Okay, so let's just add a little bit more room here. And so this is equal to 16, that's 48 over 3 minus 16 over 3 is 32 over 3. Integrate. Evaluate. And so you get 64 over 3. 64 pi over 3. Okay. Let me do problem number 30. In exercises 29 through 30, evaluate the integral by changing to cylindrical coordinates. Oh, okay, so we start with rectangular coordinates, and now I want to change to cylindrical coordinates. Okay, so let's do this. First, notice that x squared minus y squared is r squared. So I can change 9 minus x squared minus y squared to 9 minus r squared. This is dz, so let's keep this as dz. And then, well, I'll do dr d theta. So now, notice here that I have that y goes from 0 to, so if I look here, maybe what I'll do is I'll actually draw a picture first, if I can. Okay, let's see if I can move this down for a second. Let me actually draw a picture. So I'm integrating something. Let me just do the projection. So if I look here at my projection, y goes from 0 to rad 9 minus x squared. In other words, this is x squared plus y squared is 9. And so this is just the upper half of a circle centered at the origin of radius 3. X goes from minus 3 to 3. Therefore, this region here is just the upper half of a circle. So I have that this is the upper half. So the radius goes from 0 to 3 because, well, this has a radius of 3. But my theta doesn't go from 0 to 2 pi. It only goes from 0 to pi because it's the upper half of a circle. So because it's only the upper half of the circle here, to do part of it. So since it's only the upper half here, doesn't look too bad. And so this is just going to be the integral from 0 to pi. Now, what's inside here? Well, x squared plus y squared is just r squared. The square root of r squared is r. But I have always still multiplied by r, so this becomes r squared. So let's integrate this. And so this is equal to integral from 0 to pi, 0 to 3. Integral of r squared is r squared z between z equaling 0, z equaling 9 minus r squared, dr d theta. Okay, so let's plug in for z, 9 minus r squared. And so this becomes 9r squared minus r to the 4th. Plug in 0, well, you just get 0. So I'm just going to subtract out 0. That doesn't do anything. Dr d theta. So let's integrate this. So this is equal to integral 0 to pi of 3r cubed minus 1/5 r to the 5th evaluated between r equaling 0, r equaling 3 d theta. And so this is equal to integral 0 to pi. 3 cubed is 27 times 3 is 81 minus 1/5, 3 to the 5th is 243 minus 0, which is 0, d theta. So this is equal to 405 over 5 minus 243 over 5 is 162. Let's 162 over 5 d theta. And so lastly, this is 162 over 5 theta between 0 and pi, which gives you 162 pi over 5. And that is your answer.